Welcome! I am Karen McFarland, the punk rock professor, and I am here to give you clear and concise tools to help you crush chemistry. I'm so glad you're here, and let's get going. We're going to be talking about Lewis dot structures and specifically on neutral molecules. So we'll talk about two of them. We're going to go through CO2, carbon dioxide, and SF4, sulfur tetrafluoride. All right, so the first thing you are going to want to do anytime you are looking at Lewis dot structures, you need to have a periodic table handy. So I've got mine over here. Make sure you have yours, and let's go through this together. Okay, so for CO2, all right, so the first thing we do is we look at the molecule itself and we are given what the formula is. We know there's a carbon, we know there's two oxygen atoms. So the first thing we need to do is decide how are these bonded together? Which is the central atom? And while it's true that very often the central atom is the first one that's listed in the formula, it is not always the case. So the first thing you have to do is when you decide which is the central atom, look at which one is the least electronegative. All right, the most electronegative atoms are always on the outside. All right, so electronegative atoms, they are very good at drawing electron density towards themselves, and they are better at hogging all the electron density if they are on the outside of the molecule. So that's where we're going to start with CO2. We're going to put carbon in the center, and it will be bonded to those two oxygens. So we'll start out with, I call this a skeleton structure, and that's sort of our baseline where we will begin. Okay, then another reason why we want to have a periodic table handy is that we want to know how many valence electrons are involved for each of the elements that are there and overall for the whole molecule. Okay, so we look at our periodic table and we decide how many valence electrons does carbon have. Okay, so you take a look and you see, maybe you already have it in your mind, but it is going to be 4. Okay, so 4 electrons. I put a little E with a minus sign, my symbol for electrons. Okay, we're tallying up all the electrons in the molecule. So there we have carbon, and then again we look at the periodic table and we look at oxygen. How many valence electrons does oxygen have? So take a look at that and you'll see, yes, there are 6. Okay, so the oxygen atoms. I hate putting oxygen here, it looks like a big 0, but these are the elements, all right? And each oxygen has 6. So we've got 2 of them, and there are 6 electrons, so that gives us a total of 12 valence electrons the oxygens are contributing. Okay, so there's our 12 electrons. There's only 1 carbon, so that gives us the 4 electrons from carbon. And we add up all those valence electrons for the molecule, and there are our 16 electrons total. That's what we're going to work with for this molecule. All right, so this molecule can have no more or no less than 16. And so often it's tempting to just start putting electrons around, just trying to make sure everyone has their octet. But no, we only get 16 to work with. Okay, so this is a starting point. We already started out here where each one of these lines is a single bond. Each single bond is 2 electrons. So we have already used up 4 electrons of those 16 just by creating those bonds. Now we're going to put the rest of the electrons around. And the rule of thumb is you always put the electrons around the periphery, around those outer atoms. Again, thinking about their electronegativity, they're going to want the most electrons. We might not end up that way, but that's where we're going to start. Okay, so let's put all the electrons that we can around the oxygen atoms. Let's count while we're doing this, okay? So 2, 4 is where we started. 6, 8, 10, 12, 14, 16. Okay, that's it. There's all of the valence electrons. But now we've got to check, does everyone have their octet? Oxygen, 2, 4, 6, 8, yes. Carbon, 2, 4. No way, carbon doesn't have nearly, it only has half of its octet. This oxygen is fine as well, but we've got to give carbon its octet. So this is where we are allowed now to move electron pairs and have them shared by the two atoms here, so that oxygen still retains its octet, but now we're giving more electrons to the carbon. All right, so when we do that, I'll rewrite this, and we create this double bond here. And I'm going to keep these two pair right here. By the way, you can put these pair anywhere. It doesn't matter. I could have put them there as well. This is just a bookkeeping, just keeping track of all the electrons. Okay, over on this side, okay, this oxygen had its 8 here. The carbon only had 4, and so far it has 6, but we can do the same thing on the other side with that other oxygen having a pair be shared between the carbon and the oxygen there. Okay, now we double check again, make sure everyone has their octet. Yes, 2, 4, 6, 8 around the oxygen, yes. 2, 4, 6, 8 around the carbon, yes. 2, 4, 6, 8 around that oxygen. Ta-da, we are done. Okay, yay for carbon dioxide. Okay, so there's our Lewis dot for that one. One more example we're going to do, and that is for SF4. All right, so we're going to follow this same kind of procedure, get a skeleton structure, count up all the electrons, distribute them around. Okay, so let's see what this one looks like. Again, we consider which one is the least electronegative. Sulfur, of course, because fluorine is so electronegative. It is the most electronegative atom element on the whole periodic table. So we know sulfur is going to go in the middle. So we put our sulfur there. And we put those 4 fluorines around it. Okay, next we are going to make sure that we have all of the electrons accounted for that are contributed by all 5 of these atoms. So we get our periodic table handy, we look where sulfur is, it's in group 6A, 6 valence electrons, so we've got that. There's only 1 sulfur, so that's going to contribute a total of 6 electrons. We have, in terms of fluorine, we've got 4 of them, and there are 7, okay? So that gives us 28 electrons from the fluorines. We add those all up, and we get 34 total valence electrons that we're going to be working with here. Okay, how many have we put up so far? We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Okay, we're done in terms of filling octets, but this molecule has 34 valence electrons. That means we have a pair of electrons that has to go somewhere. Where does it go? Well, sulfur can expand its octet. It is one of those elements that can do that. Okay, once you're in the 3rd period and below, all of those nonmetals can expand their octet. And so we're going to take that pair and we are going to put it right in there on that sulfur. And now we can check our octets. 8, 8, 8, and yes, sulfur has 10, but that's okay. It can handle it. All right. That's it for this one. Thank you so much, and I hope this was helpful for you. If it was, like, subscribe, ask any questions you want, and you have done great. So keep in mind any other kinds of chemistry problems you might want to do. I might be doing them here. They're going to unfold with time. And now you have earned, any of you who are still with me, you've earned your bonus track. So I wanted to tell you about my t-shirt and a song I want you to listen to. Agent Orange, awesome band. I saw them so many countless times in the 90s in Santa Barbara at Toe's Tavern and place. They're so much fun. And they have a song called It's All in Your Head. And so I hope all of this is now in your head. Good job, and I'll catch you later.